Hello again. In this video, we'll be starting to think about what can a single sample tell us about an entire population. That is starting to think about statistical inference in the context of simple linear regression. I do want to point out that this video applies to homework 9. So if you haven't already, I would recommend you finish homework 8 before you are exposed to these new topics in this video. All right, here's our learning objectives, and we'll check in at the end to see how we did on addressing each of these points. All right, so in the previous two videos, we were doing simple linear regression, but we were essentially describing what happened in a particular sample. So we fit a sample regression line to some data, could describe the slope and the intercept of that line, describe the fit of the line, and use the line to make predictions. Well, now we're going to think about, taking sampling variability into account. What formal conclusions could we draw for the entire population that is represented by this sample? So we're going to make some inferences, using sample statistics to make a conclusion about population parameters. Now, as with other inferences in the course, we have to check that certain conditions are met or state certain assumptions that are going to be made. So linear regression has quite a few assumptions. There's actually 5 that we need to make. So by the end of this video, you'll hopefully be able to name all 5, and there are 4 of them which we'll be checking with the data. So you'll become familiar with how to produce the appropriate plots and check if these assumptions are reasonable or not. All right, if the assumptions are reasonable, there's actually quite a few things we can do with linear regression, and that'll be the topic of the next video. All right, so we saw before 2 videos ago that the sample regression line is going to use a sample slope, B1, a sample y-intercept, B0, and in conjunction with a particular value of x, we can predict y. And that line was placed to minimize the sum of squares error for the bivariate data pairs in our sample. Well, B0 and B1, those are simply sample statistics then. They were fit using just the data in that one sample. However, they're going to serve as point estimates for the population parameters. So beta naught, like the Greek version of B, beta naught is the y-intercept of the population regression line. And beta 1 is the slope of the population regression line. Particularly the slope is going to be of the utmost importance in the upcoming video, because the slope is the rate of change between x and y. This whole analysis is about how does x relate to y, and there it is, it's right through that slope. All right, so the population regression line with those parameters, beta naught and beta 1, that would be the line that minimizes the sum of squares errors if you had the x value and y value for every single individual in the population. Okay. And that line would represent the mean value of y at a given value of x. So that's what this notation here represents. So mu for population mean. And then from probability, from probability, you'll recognize this notation with the vertical line. So the vertical line means given. So it's the mean y at a given x. And that value would be represented by the height of the regression line, which could be found by those population parameters with the slope being multiplied by x. Right? So that's the population regression line indicating the mean value of y at a given x. Closely related, but a little bit different, is our simple linear regression model. So here, rather than the mean value of y at a given x, we're indicating what is the exact value of y for a given individual. So for that exact value, you can think of it as, well, the population regression line would get you in the right neighborhood. But there's going to be scatter around the population regression line. So any given individual might be above or below by some amount. And that amount here is represented with an error term. So this is the Greek E, or epsilon. So this is the error associated with individual I. Okay, so the heart of this expression is the same for both equations. Just when we add on the error term, we're then being specific and talking about a single individual rather than the mean tendency. All right, so here's an idealized case of what this model posits is going on for the population. So we have a regression line, and in this case, it happens to have a positive slope. It could just as easily have a negative slope. And I've picked 3 values for x, and presumably this relationship would hold anywhere in between x1 and x3 as well. So along this region of the x-axis. What we have is a population of normally distributed values. So tilt your head to the side, or I guess it's this way for you guys. So it's a normally distributed population here at this fixed value of x. So in other words, half of the value should be above the line, half should be below because it's symmetric. The mean would be right at the line. And notice it's a normal distribution. So the peak, if you think of filling in a scatter plot around this line, the peak density of the dots should be right at the line. And then, a lot of points close, either just above or just below. But as we get farther away, the points should become less common. Okay, so it's a normal distribution whose mean is given by that population regression line, and which has some variance, sigma squared. Now, if we move over to x2, and basically you could copy and paste the same bell curve, you just have to slide it up a little bit. So now the center is at a slightly higher location, because if you were to plug x2 into the equation, and it's a positive slope here, we're going to increase the height by some constant amount. Okay, but it's still got the same variance, sigma squared. And then same thing over here. Again, a normal distribution, same spread as before, just slid upwards. And if our slope was negative, it would be the same thing, just slide downwards. All right, so that spread around the regression line is a true population variance, sigma squared. The square root of it would be some true population standard deviation, sigma. Okay. Well, we can obtain an estimate of sigma based on our data, and that is the root mean square error, or standard deviation of the errors, which we talked about in the previous video. So this describes for our sample what's the dispersion, above and below the line. So I've put in here some dashed lines that are placed exactly one standard deviation of the errors above and one standard deviation of the errors below this sample regression line. Okay, but we can think about in the population, you could do the same thing as well. So here we have these bell curves. And on a bell curve, the point of inflection here and here, those are at one standard deviation from the mean. So you could line them up, a parallel line above the regression line here and one below here. And that would be analogous to what we've done with the sample. Okay. All right, so remember that standard deviation of the errors represents the typical error in our estimates. Okay, and if we squared that, or that is, we just had the mean square error instead of the root mean square error, that would be an estimate of the true population variance. All right. So some things come out of that picture there. This is the ideal case. So what about this picture do we need to check is reasonable based on our sample data? Well, for one, these bell curves, they are lined up along a straight line. So that's one thing we're going to need to check. Another thing is notice the normal distributions and that these normal distributions are equally spread out. They have the same variance. So those are going to be some of the things we check with our data. Okay, so these are 5 assumptions you will need to know. And beyond just stating that you're assuming these things, for 1 through 4, you'll need to be able to justify your assumption based on some jump output. All right, so the first condition is that it's a linear relationship between x and y. Second, that the variance is constant across x. So that is, as we go across the plot, left to right, the spread around the line is of consistent width. Next, that our errors are independent. So remember, every individual is not going to fall right on the line. They're going to be a little above or a little below, most likely. Maybe a lot or a lot above or a lot below. But is that error independent from the next guy over and the next guy over from that? All right, then, like we saw, there were bell curves around that regression line. So at any value of x, are the errors normally distributed? And then number 5, of course, do we have a random sample? Can we count on our sample to be representative of the population? So number 5 will be something we usually just assume. It's not something that can be checked using the data in JUMP. All right, so how would we check these things? We'll take them one by one in just a moment. All right, so our errors, if we take a random sample and we have this random selection of individuals, and it's a random process, whether the errors are going to be positive or negative and how large they're going to be. But although they're random, there is a pattern. Okay. So I still have those red dashed lines at plus or minus 1 standard deviation of the errors around our sample regression line here. And I've added another set that are equally as far away, but now we're going 2 standard deviation of the errors above for this blue line and 2 standard deviations of the errors below for the lower blue line. And they're parallel because no matter where we go across the plot here, whether we're down at 30,000 vehicles or 45,000 vehicles, this depicts that the variation in the sales is roughly constant. Okay. So if it's a normal distribution and the blue lines are plus or minus 2 standard deviations from the mean, what percentage of the points should fall between the 2 dashed blue lines? All right, so the answer comes from the empirical rule. So if you have a normal distribution, about 95% should be within 2 standard deviations of the mean. It's just that now the mean is our regression line showing what's the mean y at a given x, at least, at this point, our estimate of that. And then 2 standard deviations, sample standard deviations in this case, above and below the regression line. Okay, so looking at the scatter plot, we see that the vast majority of the points are within the dashed blue lines. There's a few that aren't, but that's to be expected because we would expect about 5% for any sample to be outside. Okay, it won't be exactly 5% due to sampling variability, but in the long run, if we did this lots of times, it would be about 5%. Okay, now we get to checking these. So to check these assumptions, we're going to do what's called residual analysis. So the clues are all hidden in the residuals. So I'm going to go to jump. These are the general clicks I'm going to be doing. So first you have to fit y by x and add in your regression line. And then a new red triangle will appear down where it says linear fit. And here we're going to plot the residuals. All right, so I'm using the gas station data again, fit y by x. And since we're trying to predict the sales, that's y. We're making that prediction based on the traffic, x. All right, at present, there's only one red triangle. So use that one to fit line. There it is. So last time we talked about the goodness of fit. So we saw that about 54.9% of the variation in sales could be explained by the traffic, but that typically our predictions were off by about 1.5 thousand gallons. All right, so only after we fit the line is there this new red triangle by linear fit. So now we've got that, and we can jump to plot the residuals. So it's going to make, in this section called diagnostics plots, there'll be 5 new plots, which can be a little overwhelming at first. If we want to clean this up a little bit, we're only going to use the first, third, and fifth. So you can minimize the second and the fourth by clicking on the little gray triangle next to them. All right, so we should be left with the residual by predicted plot, residual by row plot, and last, residual normal quantile plot. All right, so what can those tell us about our assumptions? Now, I have to be honest, this next part, any one assumption is not that difficult to check, but where people get tripped up is that they start cross-pollinating and trying to use the wrong plot to address the wrong assumption. So on homework 9, there's actually going to be a problem where you have a big grid and you fill in for each assumption. What sort of plot are you looking at? What's the pattern that you want to see? And what's the pattern that you don't want to see? Okay, so focus on those things as we go through each condition. All right, so is it reasonable to assume that in the population, X and Y truly do have a linear relationship? And we've sort of checked this, at least at a glance. We've used the scatter plot because we had said back in correlation that you should only do correlation if it was a linear pattern, no curves. So same idea here. On your scatter plot, does the cloud of points seem to generally form a linear trend? It tracks the line more or less. It doesn't curve away or form any sort of parabola shape. Now, it's okay if there's lots of scatter. Scatter is fine as long as the overall picture is not a curved pattern. All right. The thing with the scatter plot, though, is everything's at an angle. So sometimes if there's a curved pattern, it may be hard to spot, especially if it's a subtle pattern. So to get a kind of zoomed in closer look, one where we don't have to tilt our head, we're going to use what's called the residual by predicted plot. So especially for a regression with a positive slope, you can think of this as like we took the regression line and straightened it out. All right. So this is showing the residuals on Y. So, due to the definition of a residual, this is, how far above or below the regression line are we? The central value is going to be 0. So on average, our regression line is in the right spot. Although about half the time we're too low and about half the time we're too high. So what we're looking for here is that there's no curved patterns. All right, so don't want any curved patterns. What we do want is just basically a random scatter on this plot. Let me give you an example of a data set that violates this condition. So on the left is the scatter plot. This was a study where they raised lobsters in big fish tanks. So they knew exactly how old the lobster was, and then they wanted to predict its size. So if you looked at the scatter plot, especially if you just did a quick glance, you might say, well, it looks like, yeah, the points are going up. They more or less track this line. But if we take the slope out of the equation, straighten it out, and also we're kind of zooming in, expanding the scatter around the line, we'd see the pattern on the residual by predicted plot that does have a curved shape, like a big general arc shape to it. Okay. So my tip when reading these plots is don't put too much emphasis on any one or 2 points. Just look for the big picture. But here I kind of see a big arc shape to it. So that would violate the condition that X and Y are linearly related. Okay, on to our second condition, which is that there's constant variance, that is constant spread, as we go across the plot. So we're also going to use the residual by predicted plot for this one. So with our gas stations, we saw there was pretty much a random scatter. And that's good because as we're looking across the plot, there's like just basically a rectangle more or less of scatter. It's equally spread out above as it is below, and the thickness is consistent across the plot. So that is that the variation or variance is consistent across X. On the right, I have an example of a data set that violates this condition. So this is predicting the price of a diamond based on the size. So as we go across the plot, it gets thicker. So it starts really close together and then it gets farther apart. So I call this a funnel shape. So that is the variation over here is small. The small diamonds are all generally pretty similar price. But as we get to the larger diamonds, the prices become a lot more variable. So this would violate the assumption of constant variance. Okay. So to recap, for constant variance, we're looking at the residual by predicted plot. We would like to see random scatter with equal thickness across the plot. What we don't want to see is this funnel shape where the variability changes as we go across. All right, next, we'd like each individual's error term to be independent from the others. Now, usually if you have independent subjects or independent gas stations in this case, their errors would be independent just naturally. That is, unless there's some artifact of how you collect the data. And most commonly, this is due to the effect of time. So that is, if you put your data in your data table in the order that it was collected, if there's some effect of time, then the values that are close to one another in nearby rows may tend to have errors that are, let's say, all negative or all positive or all of about the same size. So we don't want that. We want just totally random errors that are sometimes positive and sometimes negative and have no association with the values that are near them on the plot. All right, so to check this, and you can only check if your data table is laid out in the order that it was collected. So we're checking here, is there any artifact of time? Okay, so I'm examining my data table, and it doesn't appear that either variable was sorted. That is, my traffic is not going from smallest to largest or vice versa, and neither are my sales. So if there's been no sorting taking place, it's going to be reasonable to assume then that these were in the order of collection. And therefore, I can use the residual by row plot to check for any patterns. Okay, now what do they mean by row? They mean literally the row in your data table. So row number 1, the first gas station is going to be off to the left. And then row number 80, the last gas station, is off to the right. And then on the y-axis, they're plotting the size of the error or residual. All right, so what we want to see, if the errors are just totally random, is we want to see just totally random zigzags. Sometimes up, sometimes down, sometimes a little, sometimes a lot, but no general pattern. And it does this with the dots connected in a time series, because, we're sort of thinking about if these were collected in this certain order. All right, so what we want to see is just random zigzag pattern, and that seems to be the case here. What you would not want to see is any trend where there's a slope, either going down or going up, that it's consistently moving, up or down. We don't want that. We just want random zigzags. All right. If your data table had been sorted, smallest to largest, and you moved around the order of the points, maybe just to on your real estate project, you move things around to color code them or whatever, you wouldn't be able to use this method to check. So hopefully you keep your original data table format somewhere so that you can use this residual by row plot. All right, next. Remember the bell curves that were lined up along the regression line? Well, we'd like our errors to be normally distributed as we go across the plot. So the quickest and easiest way to check this is with the residual normal quantile plot. So that was the last of the 5 plots that JUMP made. Okay, so bit of review here. What does it mean if the points line up? What does it mean if they're in a curved pattern? Well, the linear pattern is what we want here. So a linear pattern here represents the errors are normally distributed. Okay, careful, because there's that linear condition about our x and y linearly related, which we check on a different plot. But here, it's all in the name. Residual normal quantile plot. So are the residuals normally distributed? So in this plot, looks like the points more or less follow the straight line. They don't curve out of bounds. So I would say a normally distributed population of errors is reasonable based on that pattern. We wouldn't want to see a curved pattern or one where there's points out of bounds. All right, if you want to check a little more in depth, we can save the errors. So let me get a jump here. All right, so again, we have to fit the line first, and then it's that lower red triangle next to linear fit. And if we go down here, somewhere in here, there it is, save residuals. Do that. And now, if we look at our data table, it's here somewhere, we have a new column that's all the residuals. Remember, residual is another way of saying error. So we learned how to calculate errors in the, second video? So that would be, if x is traffic and we put this value, 33.6, into our regression line equation, we'd come up with a predicted value. And then we'd see how far off was the actual sales from the predicted. Okay, so here it looks like the actual sales were greater than predicted by this amount, by 0.024. Okay, so you know how to calculate these errors or these residuals. We did one in the previous video. You hopefully did 2 on homework 8. It's just that JUMP now can calculate all 80 of them in just a few clicks. All right, so are those normally distributed? How would we check? Well, just like any other column of numbers, we can analyze that distribution. We did this with ANOVA, actually. We thought, well, rather than checking each group separately, why don't we lump them all together, pool them all together, that is, and check for a normal distribution. So we're doing the same thing here. Okay, so I'm analyzing the distribution of the residuals. So I would say that it looks pretty darn bell-shaped. We have one outlier, but it's very mild. It's just past the whisker. I'm not going to bother doing a normal quantile plot because we just saw that. That was already produced by jump on the regression output. But if, say, we wanted to do a Shapiro-Wilk test, we could do that by adding in the continuous fit here normal. And then on that new fitted normal section, goodness of fit. All right, so our Shapiro-Wilk p-value for these residuals is 0.801, well above 0.25. So normality would be a good assumption for this population of residuals. Okay, and that confirms what I already suspected based off of our normal quantile plot, which had a, generally straight line pattern. Okay, so like I said, checking the assumptions is not that hard if you know what you're looking for. So you have to be on the right plot, and you have to know what you're looking for. Do you want random scatter or a straight line or what is it you're looking for? So if you get stuck, just feel free to rewind the video, go to the appropriate section. But by now, we should be able to distinguish between descriptive linear regression, so it's basically videos 2 and 3, versus inferential linear regression, where we're going to start talking about what can we say about the whole population based off of just a sample. So right now we're sort of gearing up to do that. We can only do that if certain conditions are in place or certain things can be assumed. So this video was all about checking those assumptions. All right, we'll see you in the next video where we actually will get to make some population level inferences based on these assumptions that we've just made.